Okay, let's do some binary multiplication and division to wrap up our discussion of binary arithmetic. We're going to see that the easiest way to do binary multiplication and division is by shifting the bits left and right. And so if I start out with a number that looks like this, so I've got a pretty long binary number here that would be pretty hard to multiply, but if I'm going to shift it 2 places to the left, I'm going to multiply it by a factor of 4. Let's prove that by shifting this number 2 places to the left. So before I shift, let me first of all copy the original number 001, 001, 0111. And since the whole point of this is to prove that the number gets multiplied, I'll go ahead and do the conversion by hand. So this is 1 plus 2 plus 4. There's 1, 2, 4, 8. There's 16 plus 16. 32, 64. There's 128. There's 256, 512. And then the last one is 1024. And this number works out to be 1175 in base 10. Now when I shift the number, I'm going to shift zeros in as I come in. So let's first of all, I'll shift in 2 zeros, and then 1, 1, 1, and then 0, 1, 0, 0, 1, 0, 0, 1. And so, for example, this 1 became that 1, this 1 became that 1, this 0 became this 0, and ultimately that 1 became that 1. And these 2 zeros here fell off into what we call the infinite bit bucket. They just went away forever. And so if I do this conversion, I have 1, 2, this one is worth 4 plus 8 plus 16, and then 32, 64, then 128, 256, plus 512, 1024, 2048. The last one is worth 4,096. And that works out to be a total of 4,700 in base 10, and 1175 multiplied by 4 is, in fact, 4,700. So that's the correct result. Let's see if we shift to the right. Do we divide? So I have a different number this time. So I'm going to start out with 101, 001, 011 in base 10. This is 1 plus 2, no 4, but there is an 8, no 16, no 32, but there is a 64, no 128, but there is a 256. And so that number works out to be 331 in base 10. Let's shift this number 2 places to the right. And as I do that, then these 2 bits are going to fall into the infinite bit bucket. That's just a silly name that we give to the place where those bits disappear. And so the 0 is going to become the least significant bit. And then I have a 1, 0, 0, 1, 0, 1. And I shifted 2 zeros in, so those are new. But each of the other bits just shifted 2 places to the right. And if I consider this number, this is going to be a 2. Whoops. There is a 2 plus there's no 4, no 8, but there is a 16, no 32, but there is a 64. 2 plus 16 plus 64 yields 82. And that'll be in base 10. And let's double check this. And so 331 divided by 4 would give me 82.75 in base 10, which is almost 82. And the problem that did kind of hint that something weird was happening. Did you discover any special cases that need to be considered when shifting to the right? Well, if the number is not evenly divisible by 4, then it's going to round down to the nearest integer. So if we take the 82.75 and we round it down, we don't round it to the nearest integer, we round down, then this approximately equal becomes equal. So be aware that when we shifted these 2 bits right here out of the number into the infinite bit bucket, we lost information, and that information was the 0.75 that we dropped. We're still doing division, it's just that we're doing division rounding down to the nearest lower integer. How would you use shifting and adding to multiply a binary number by 20? Well, if I wanted to do 20 times x, I need to compose that of powers of 2. So that's going to be 16 times x plus 4 times x. So I can get 4 times x by shift left twice and store 4x. So now somewhere, presumably off in memory, I've stored 4x, and the number now has been multiplied by 4. Let's shift left 2 more times. Shift left twice more to get 16x, and then add that new number plus the thing that we just sent off into memory, 4x, to get 20x. So while the shifting only really gives us the ability to multiply by powers of 2, we can use various combinations of the shifting and adding to multiply by any integer number.